Atomic force microscopy, AFM, is a powerful technique used to study surfaces at the nanoscale by analyzing their topography, mechanical properties, and various other surface interactions. AFM operates by using a sharp probe, typically at the end of a cantilever, to scan a sample surface. The interaction between the probe and the sample surface provides information about the surface features and properties. Probe and cantilever. The heart of AFM is the cantilever, which is a thin, flexible beam with a sharp probe attached to its free end. The probe is often made of silicon or silicon nitride and is extremely sharp, with a radius at the nanometer scale. Feedback mechanism. The cantilever with the attached probe is brought close to the sample surface. As the probe gets closer, the interaction forces between the probe and the surface become significant. These forces include van der Waals forces, electrostatic forces, and repulsive forces due to the overlap of electron clouds. Scanning. The AFM probe is raster scanned across the sample surface in a controlled manner. The motion of the probe is precisely controlled by piezoelectric scanners that move the sample in the X, Y, and Z directions. As the probe moves, it follows the surface contours, experiencing varying forces due to the surface topography and properties. Cantilever deflection. The interaction forces between the probe and the surface cause the cantilever to deflect. This deflection is usually measured using a laser beam reflected off the back of the cantilever onto a position-sensitive photodetector, PSD. The deflection is directly related to the interaction forces between the probe and the surface. Feedback control. To maintain a constant force or deflection, AFM uses a feedback mechanism. The feedback loop adjusts the vertical position of the cantilever as it scans the surface, keeping the cantilever deflection constant. This results in maintaining a consistent interaction force between the probe and the sample surface, which is essential for accurate topographical mapping. Data collection and imaging. The deflection data collected from the photodetector as the probe scans the sample surface is used to create a topographical map of the surface. This data can be processed to generate 3D images that reveal the surface features with nanometer-level resolution. Additional modes. AFM can be operated in various modes beyond topographical imaging. These modes include tapping mode, gentler for delicate samples, force spectroscopy, measuring mechanical properties, and magnetic force microscopy, mapping magnetic properties. Overall, AFM's ability to provide high-resolution imaging and characterize nanoscale surface properties has made it an indispensable tool in fields such as materials science, biology, nanotechnology, and more.